I will now talk about two other rules for counting, basic rules but with powerful applications, the sum and subtraction rules. And they basically talk about when I'm trying to count the cardinality of a set, let's say set A, and that set A can be written as the union of two sets. And there are two different cases when these two sets are disjoint, that their intersection is empty, or these two sets share some elements, and then we have to apply two different rules for them. So the sum rule says that if you can write A as the union of two sets, the union of n sets, these sets are disjoint, pairwise disjoint, no two of them share any elements, then the cardinality of A is the cardinality of A1 and A2 and so on. You take the sum of them. So if this is, if this is really the Venn diagram, that this is A1 and A2 all the way to AN, and this is A, is the union of all of them, it makes sense that when we try to count the number of elements in A, it's the number of elements in A1, plus the elements in A2 are different from the elements in A1, so I can add their number. The elements in A3 are different from the elements in A1 and A2, so I can add their number, and so on, all the way to AN. Okay? So this is the sum rule. It has very powerful applications, so let's look at an example here. Suppose I want to count passwords, and the passwords here can be between, their length can be between 6 and 8 symbols. The password can be of length 6 or 7 or 8. And the first symbol must be a letter, lower or uppercase, and the remaining symbols, the second, the third, and so on, can be either a letter or a digit. Okay? So now, since the passwords can be of length between 6 and 8, and A is the set of all passwords, then I can write A as the union of three sets, 6 and 7 and 8, where AI is passwords of length I, right? Now look at these, that they are three pairwise disjoint sets. There is no password whose length is 6 and 8 at the same time, or 6 and 7 at the same time. So these are really disjoint sets. And the sum rule tells me that the cardinality of A is the cardinality of A6 plus the cardinality of A7 plus the cardinality of A8. So now what's left for me is to count each one of these three terms here. And now let me look at A6, for example, the cardinality of A6. A6 is passwords of length 6. So let's actually, before the cardinality here, let's reason about this set A6. It's password of length 6. What we are saying here is that the first element must be one of these 52 letters. So here, in this first place, we can put any of the 52 letters, okay, upper and lower case. The remaining symbol can be letter or one of the 10 digits. So this one, the second one, can be any of the 52 letters or any of the 10 digits. So we have 62 possibilities. The same thing with the third, fourth, fifth, and sixth. So here the cardinality of A6, using the product rule, it is 52 times 62 to the fifth. Using the same reasoning, the cardinality of A7, the first one has to be 52. There are 52 possibilities. And the remaining 6 can be any of the 62 letters or 62 symbols. So it's 62 to the 6. And A8 is 52 times 62 to the 7th. Okay? So now the cardinality of 8 is the sum of these three numbers here. Okay? So 52 times 62 to the 5th plus 52 times 62 to the 6th plus 52 times 62 to the 7th. Okay? Again, key issue here is that A6, A7, A8 are disjoint. Now, what happens if they are not disjoint? The subtraction rule talks about that, but now I will talk just about the case of two sets. Okay? So subtraction rule, imagine that you have set A that is of this form here. So this is A1, this is A2, and this is A. I'm writing it as these two sets here. If you look at A1 and A2, then A can be written really as the union of three disjoint sets. One of them is this region here, One of them is this region here, and one of them is this, right? So these three regions are disjoint. Okay? So now what happens if I take the cardinality of A1 plus the cardinality of A2? If I say A is the cardinality of these two using the sum rule, then for every element for every element in the blue region here, it is fine. We counted it, every element there was counted once because these elements belong only to A1. Every element in the green region here is fine. We counted it once because it belongs only to A2. The problem is when we go to elements in the orange region here, we counted them twice because we counted them when they are element of A1, when we took the cardinality of A1, and we counted them a second time when we took the cardinality of A2. So to fix this, so we take the cardinality of A1, cardinality of A2, this sum has double counted every element in the orange region. Let's actually remove one for every element in that orange region. How many elements are there? It is the cardinality of the intersection of A1 and A2. And this is where we get the subtraction rule, okay? This can be generalized to more than two sets, and we will talk about that in a different video. Let's look at an example of the subtraction rule here. A valid password is a sequence of 8 symbols, each of which, now we have 8 symbols only, okay? It cannot be 6, 7, or 8, it's 8 symbols, each of which can be a letter, lower or uppercase, or a digit, 0 to 9. What's the number of different possible passwords that either starts with A or end with Z? So now, if I look at A1 as the passwords that start with A, and A2, the passwords that end with Z, A1 and A2 are not disjoint. Why? Because A1 intersection with A2 is the set of all passwords that start with A and end with Z. Okay? So now if I want to look at the cardinality of A, I need to compute the cardinality of A1, cardinality of A2, and then subtract the cardinality of the intersection. This is a subtraction rule. What is the cardinality of A1? It's the set of all passwords that start with A. So these passwords start with A. They are of length 8. This is A. Then we have a second, third, fourth, fifth, sixth, seventh, and eighth. The first one is A. I have no choices there. I cannot say it's any of the 52 letters. No, it has to be A. But any of the other 7 can be any of the 62 symbols, the 52 letters or the 10 digits. So now for this one here, we have 62 to the 7th. Using the same reasoning for the A2, the last one has to be Z, but the other 7 here can be any of the 62. Okay, so we have to count this, the 62 to the 7th plus 62 to the 7th. Now what about the intersection here? What are we saying in this intersection? That the passwords have to start with A, have to end with Z, and then we have any of the other 6 symbols here, right? So this is 62 to the 6th. We need to subtract that. So this is the number, or the number of passwords of length 8, where every symbol is a letter or a digit, and the first letter is either A or either the first letter is A or the last letter is Z, is 62 to the 7th. This is the number of passwords that start with A, plus 62 to the 7th. This is the number of passwords that end with Z, minus 62 to the 6th, which is the number of passwords that start with A and end with Z. We need to subtract that because these passwords have been counted twice when we took the cardinality of A1 and the cardinality of A2. So this is an application of the subtraction rule. Notice that in both applications of the sum and subtraction rules, I am of course making use of the product rules. Okay, so in general, counting problems, we are going to be using a combination of rules when we are doing the counting itself.